But you're not going to tell us about the linear potential stuff, right? You skipped over that, it sounds like. Your experiments in the tilted lattice.
Yeah, actually, I thought I might have time today to go back to it.
I'm pretty curious to hear more about this.
Yeah.
I know, this whole, is this related to NBL, Stark localization, or is it related to fracton physics? And I know we briefly mentioned these things. Hear more about this.
Yeah.
I know, this whole, hey, Leo.
Hey.
NBL, Stark localization, or is it related to fracton physics? And I know we briefly mentioned these things. Hear more. Thanks, Leo. Yeah, that was just echo from the Boulder. He turned on the YouTube, so we're live. We'll still wait a couple minutes, but. So you said you and David had talked about the connections to like fractons and Stark localization and different things, right?
I mean, the stuff we did wasn't fractons. It seemed that we would have to go to very large tilts in order to get into a fractonic Hamiltonian, where the dynamics would just be too slow. But
I see.
The Munich group did this in 1D, and there it seems like you could get into that regime more easily.
Mm-hmm. Yeah, that's right. I forgot about the Munich paper. I haven't actually read the Munich paper, but I remember seeing the.
Yeah, I mean, our lattice has this weird property that it's kind of hard to get into 1D systems. That's why everything we do is in 2D, the bow tie geometry.
I see. But that was kind of just what we overlapped in Durham briefly there for a few days, right, at this conference. And I think you'd mentioned you were thinking about this, but I guess you just.
Yeah, we tried it a bit, but then it just, like I said, the tilts we needed, I mean, we can produce the tilts, but by then the dynamics are just incredibly slow.
Gotcha. Hi, Leo. Probably people will be a little bit later today. Our morning session went quite long, so
okay.
So I think they'll probably need a little bit of a break. And Waseem, are you going to be able to make the discussion this afternoon for additional questions?
Sure. Yeah.
Great.
How long is that?
You don't have to attend the full time if you have constraints, just let me know, but it's a sort of nominally an hour and a half starting at 2 Boulder time.
Mm-hmm.
And it's just, after people have a chance to reflect on the week, all the lecturers hopefully join and we can have a discussion. Good. So I think this is probably, we're still a little low, but I think maybe start a little slow and remind us of where you stopped last time, Waseem, and you're good to go. So take it away.
Yeah. So this is the third lecture in the series. And the first lecture was looking at, we talked about how to build a quantum gas microscope, the nuts and bolts of it. And then we looked at systems at half filling, mostly antiferromagnets, candid antiferromagnets, etc. And then in the second talk, we started looking at doped systems, but with conventional probes. Even though we were using microscopes, we were just using them mostly for their ability to pattern on small length scales and their high signal to noise. But the kind of experiments we were doing were, like ARPUS or transport, the kind of things you would do in conventional Kness matter. And now in this talk, after a brief detour backwards, I'll continue to just doing, using the microscopes as microscopes to look at correlation functions and so on in doped systems. So yeah, I'll go. There's just one last topic I wanted to. I touched on last time with transport, but I didn't have time to go into detail and so today I'll do that and then we'll move on. Okay, so we talked about transport of charge in doped systems, and there we saw this strange metallic behavior. We talked about transport of spin in Mott insulators, these experiments from Martins Wehrlein, where they measured spin diffusivities. And then I mentioned that in experiments in my group, we also measured transport of heat in these systems. And it's kind of challenging in an experimental setting to produce heat gradients in the system in a controlled way. So here what we did was we actually found a nice trick to convert a density modulation into a heat modulation, into an energy density modulation. And the setup is very similar to the setup we considered last time. Just start with a Hubbard system and imprint using a spatial light modulator, put on it a charge density wave. And now the additional ingredient is going to be introducing a large tilt. And the tilt in this case is going to be a large tilt along one of the lattice axes, and this is very important. It turns out when you move the tilt away from the lattice axes, the physics can be very different. So when the tilt is along a lattice axis, then you have energy constraints along that axis. Remember, these are closed systems. There's no dissipation. So if your naive thinking might be, okay, I put atoms on a hill, they might want to fall downwards. But of course, now the system conserves energy. So if a particle moves downwards, losing some tilt energy in the large tilt regime, then some other particles have to move upwards to keep the energy of the system constant. So, but this is true in the tilt direction, but in the other direction, of course, the fermions are free to move freely. So connecting to the topics you've learned about before, this movement along, so let's say the tilt is along the horizontal, the movement along this vertical direction is what allows thermalization of the system, because there's a large bath of fermions along that direction in this interacting system. Whereas if you, let's say, pointed the tilt along some arbitrary direction, so you had constraints along both directions, then you lose this bath. And even though the system is clean, you can have things very similar to the many-body localization you learned about. So the system, now due to these constraints, can be non-ergodic. And this is not a topic I'm going to talk about, but there have been some experiments in one dimension from the Munich group doing this type of stuff. Okay, so yeah, so the tilt is in this direction, and now we're just going to start with this initial charge density wave and ask, how does the system thermalize? And indeed, we do find that it thermalizes. So after a long time, we get a uniform density distribution where we've lost this modulation. Okay, so this sounds like a charge transport problem, but what I'm telling you is that this is actually going to be connected to heat transport. Let's see how that works out. So let me first show you data that's kind of more similar to what we've seen before. So in the untilted system, this F here is going to be the bias between neighboring sites. Let's say we have tilt 0 and some moderate interactions. And what you see is that as a function of time, the amplitude of this modulation decays exponentially. And here I'm showing it for different wavelengths. So this is a short wavelength, longer wavelength, and so on. And you can just fit exponentials and extract a time constant for this decay. And what you find is that this time constant goes quadratically with the wavelength. So this is exactly what you expect from diffusion. So how does this change now in the tilted system? Well, first look at the x-axis. Everything is much slower. But then the other interesting thing is that we find once we fit these exponentials is that the time scale goes like the 4th power of the wavelength. So this is very subdiffusive transport. And diffusion is so generic. So here, this is exciting. We would like to understand what's causing this transition from diffusion to subdiffusion as we increase the tilt in the system. And just to emphasize this a bit more, so this time scale goes like some lambda to some power. And here's the power shown measured as a function of this tilt that we're applying. So you see, once the gradient is on the order of the tunneling, we see a sort of a crossover from a diffusive behavior to a subdiffusive behavior with power low 4 now. Okay, so let's try to understand this in a few steps. So I told you this is a system that indeed thermalizes because of the presence of this bath in the direction orthogonal to the tilt. So once the system undergoes local thermalization, then we can talk about a local density, a local temperature. And then we will have to, we can write a hydrodynamic theory, which then allows these quantities to relax. So the first step is the local thermalization. Let's understand how that happens. So we start with this charge density modulation. And what happens actually is what you might expect. The atoms just slip down the hill in the beginning, but they don't go very far. How far can they go? So if they're slipping down the hill, then they're exchanging this tilt energy with internal energy. There's some energy flowing from the tilt to the internal energy. And this is a closed system, so it wants to maximize its entropy. So it wants to heat up to infinite temperature. So now you can ask, in this infinite temperature state, so this is actually an infinite temperature state within a single band Hubbard model. We see in the experiment that we're not exciting any higher bands. So there's an amount of energy per particle in this infinite temperature state after the atoms have slipped. And that amount of energy is on the order of, the microscopic couplings T or U. So when how far can the atoms fall? Well, the F, the bias between neighboring sites, times the distance it falls has to be on the order of that energy, T or U. And since I told you we're looking at U and T on the order of F, this slip has to be on the order of one site. Okay, and indeed that's what we observe in the experiment. Within a few tunneling times, like 10 tunneling times or so, we see a phase slip on the order of a site as the system reaches this local thermalization, as it does this local thermalization where it heats up to infinite temperature within a single band. Okay.
I have a question about the tilt part. So you said that the atoms don't fall very far and they can't gain a lot of kinetic energy. Is that because they're restricted to a band? Like if they could go to higher bands, then they could gain any more energy.
It's precisely because I mean, all these quantities are small compared to the band gap, and they're not going to higher bands. So there's a maximum amount of energy that you could have in this at infinite temperature in this single band model.
I see. And why is it that they don't excite a higher band?
It's possible that they do that at on longer time scales. We just don't see that happen over the time scales we probe in the experiment.
I see. And the tilts are like small compared to the band gap, or the gradients are small. Gotcha. Thanks.
Any other questions? Okay, so now we have the system at infinite temperature in the single band, but it still hasn't undergone global equilibration because we still have this charge density wave. Okay, so let's think what happens when we've locally thermalized. So we have this charge density wave, and we are in a tilted potential. And now the claim is we're in local equilibrium. So you see in this charge density wave, there are regions where there is a positive slope of the density, and there are regions where there's negative slope. And the positive slope, it means there are more atoms up the hill than down the hill. So this is a weird situation when the system is in equilibrium. This is what you would describe with a negative temperature. Whereas here, you have more atoms down the hill than up the hill. This would be a positive temperature situation. So it's more natural, of course, here, since we're talking about being close to infinite temperature, to talk about the inverse temperature, beta, which is now going to be around 0. And sometimes beta will be negative, as in here, and sometimes beta will be slightly positive, as in here. Okay. So basically, this beta goes like the gradient of this density. And yeah, so what has happened is after this local equilibration, this density modulation has been converted, is now accompanied by an energy density modulation, this modulation of beta. And this modulation is now off by 90 degrees. And this, I can tell you, is what you might expect theoretically, and indeed it had been predicted in this paper here, but it's also what we see in the experiment. So now we can actually use the fact that we can measure things with a microscope on a single site. We can measure, for example, the density on a site, and we can measure say the double on density. If you take any two such quantities, you can construct a thermometer out of them. And it's easy to, this thermometer is an easy thermometer because like we're working near infinite temperature, so you can just do a high temperature expansion and you can convert this ratio into a temperature. And indeed, this is what we've done here. And this is a beta measured, these data is measured, this beta wave now is measured from the experiment, and it agrees with what we expect. Okay, so now you see what we have to do is not only relax the charge, but also relax the energy density in order to approach global equilibrium. And so now we can start to think about writing a hydrodynamic theory. So we're going to need to flow heat currents, which is this current of energy density here, JE, in order to relax the beta wave. And this is going to be diffusive. So it's going to, this is like the fixed law, but now for the energy current, this is the gradient of the energy density. And this energy is just the non-tilt energy. We're just talking about the internal energy here. And the constant here is now the thermal diffusivity. So we've encountered so far spin diffusivity, charge diffusivity. This is a new diffusivity, the thermal diffusivity that's entering into this model. And now this energy density, we can, since we're working again close to beta zero, we can do a high temperature expansion, and we can relate this E to, it turns out to be linear in beta with some, in the high temperature expansion, some coefficients, which we can compute for the Hubbard model easily, but I'm just not showing them here. Okay.
So Waseem, there are usually, or in general, there are cross terms, right, between the density gradients and the energy currents and things. So things like Seebeck coefficients. And so why is it okay to not include those here?
Well, we just didn't find them to be necessary in the experiment, but also I think we did some, a little bit of, I mean, you can't, computing this stuff exactly is hard, but we did some approximate theory, and it turned out to be they're small in this regime.
I see. And there's a question from Grace asking, can you re-explain why the positive slope in the density corresponds to negative temperature?
I mean, the system is in equilibrium, in local equilibrium, but now I'm telling you there's more atoms up a hill than down the hill. So this would be like if you were to write the, e to the minus h over kt, you would have to use a negative temperature in order to get the situation of population inversion. Okay, so now this this energy density, as we said, is linear in beta. So now this heat current is proportional to the gradient of beta, with the coefficients being the thermal diffusivity and a few thermodynamic quantities which we can compute. But I just wanted to, this is a proportionality sign here. Okay, so now once we have this, we can now write down the conservation laws to finish this hydrodynamic theory, which are the energy conservation and the number conservation. So the energy conservation law here is pretty simple. So the rate of change of energy at a given point comes from two things. One is, you can have heat currents flow in or out. So this is that. And then the second term here is just the Joule heating. So this is like an IV term here. So here you have the number current multiplying the bias between the sites. So basically, as the particles move down the hill, they're losing tilt energy and converting it to heat energy, which is causing a rate of change of E. Okay, so now we can define the strong tilt regime as this regime where all these quantities, these modulations decay slowly. So this E dot is approximately 0. And then if this is 0, these two terms are equal. And so the number current is proportional to the gradient of the energy current. But I told you the energy current already goes like the gradient of beta here. So this is the second derivative of beta. And then the beta, you remember from the previous slide, went like a gradient of n. So now this is a third derivative of the density, with the proportionality constant being the thermal diffusivity. And then there's the number conservation equation. So now if I plug in this number current into the number conservation equation, there's one more derivative, so you get an equation like this. So you see, as opposed to diffusion where you would get a second derivative, here you're getting a fourth derivative. which is why, when you Fourier transform this, you get a k to the 4, the wave vector to the 4. So this is the, the subdiffusion we're getting in the large tilt regime. And so now the nice thing is, since we know the proportionality coefficients, we can actually back out the thermal diffusivity in this infinite Hubbard model at large tilts. Okay. Any questions on this?
So Waseem, can you just a little slower explain why the strong tilt means that the internal energy change is small?
It's sort of by definition, this is what we're defining as to be like when E dot is small, then that's what we call large tilts. I mean, we have a model in the paper which kind of has the whole crossover as a function of tilt, but then the charge diffusivity enters into the story. So it's only in this large tilt regime that things are simple and you just get the thermal diffusivity as the only thing in the model.
I mean, I guess a little bit of my question is, when you say that the internal energy change is negligible, it must be that the rate of change is small compared to some other rate of change that you care about. And I'm trying to think of what the appropriate comparison to make is here. Right. So for example, I
mean, the intuition here is basically the thermal transport is bottlenecking the particle transport in the system. Okay, so in order for the charge to relax, you first have to flow these energy currents.
Yeah, I guess maybe thinking about those processes microscopically, it's pretty straightforward to see that. Yeah, okay. So there's a question from Manuel, asks, why is there tunneling in the presence of a strong tilt? Is it resonantly enhanced?
No, I mean, it's slower, but it's still there in the presence of a strong tilt. Let's see. I mean, yeah, even in a non-interacting system, you would expect that as the tilt F gets large compared to T, then the tunneling gradually gets suppressed, and you get eventually this. I mean, you get Bloch oscillations, and the oscillation amplitude will get smaller and smaller, and then you get into this regime of Wannier-Stark localization. But here the system is interacting, so it can actually, there can actually be transport.
But are you in a situation where the energy of the tilt is resonant with the energy of a state of two particles in a nearest neighboring well?
No, that's not necessary. No, we're not. You're asking about resonance with
tunneling. Yeah.
This is. I mean, there's no. Well, first of all, the tilt is F is small compared to like any band gaps. We're not in that regime, and it's not like being set in particular to match like an interaction energy or anything like that.
Okay. Thank you.
I had a question as well.
Yeah.
I remember reading that about in somewhere that if you have both number conservation and dipole conservation, then you get this lambda to the 4 like subdiffusive thing. So is it the manifestation of that? Because
no. So that's kind of a different lambda to the 4. This is like what what I was alluding to earlier. This is like fractonic regime, and we're not in that regime. So basically, to get into that regime, we need to go to much larger tilts, and sort of the prerequisite to start talking about any of that stuff is you don't even have the local thermalization happen, so you wouldn't be able to write the hydrodynamic theory. So this is really a thermalizing system which is thermalizing in a strange way, but it's thermalizing nevertheless. And what you're referring to is I mean, it's been recently probed in Munich in a one-dimensional system. There, they seem to be able to reach the tilts where they get into the regime where the dipole conservation is good, but we haven't been able to get to that in a two-dimensional system. It seems that the tilts we need are so large that the energy scales just get very small.
Mm-hmm.
So, I mean, we expect, theoretically at least, that if you could do a theoretical simulation and like kind of continue to go to higher and higher tilts, and you would have to go away from, in this two-dimensional system, you would have to go away from the tilt being aligned along the lattice axis. You would have to kind of align it in some other angle. And then you would have dipole conservation along X, dipole conservation along Y. And for large tilts, yes, it's expected you get into this another lambda to the 4 regime, another subdiffusive regime.
So it's just a coincidence that even in this case, it's lambda to the 4, but the mechanism is completely different.
Yeah, the mechanism is different here.
Thank you.
Maybe a clarification question. Should I then just think that because of the tilt, like the transport of particles is actually very suppressed and can only occur when like the internal degrees of freedom along each like direction kind of accommodate the hopping, and that's why everything kind of depends on the thermal?
Yeah, I mean, the thermalization is an integral part of the story. Have being able to thermalize along the direction orthogonal. I mean, so I can even start writing down this hydrodynamics. Okay. All right. So let me now start getting into the topic of today's lecture. This was took quite a while. Okay. So yeah, I'm gonna start by. This is mostly stuff that's not in my group, so I'm not sure I'm going to be able to answer all the questions, but I'll try. So I'm going to start with 1D systems. These are experiments that has happened mostly in Munich. And now we're going to actually be doing microscopy of these systems. So they're going to look at first the equilibrium physics happening in these 1D systems, and then looking at dynamics, focusing on spin charge fractionalization. Then we'll move to 2D systems. And so whereas in 1D, you have the spin charge separation, in 2D, you have very different physics. The spin and charge don't separate. You get these polarons. So I'm going to talk about work from, again, MPQ and Harvard, where they image these magnetic polarons, look at their dynamics. So this is all in the lightly doped 2D regime. So when you just start from a 2D antiferromagnet and say you add one hole, but then we can start to add even more holes. And this sort of starts to connect to what I talked about with transport, this strange metal. Here, they're kind of same regime, but looking at in equilibrium, at snapshots of the system. So looking at things related to these polarons, these string patterns, and looking at higher order correlation functions and seeing how one crosses over from the polaronic metal to the Fermi liquid regime. And then I'll describe some future directions, which are, there are experiments going in all sorts of directions. I'll just mostly give you Princeton's take. And I want to point out this excellent review that appeared on the, of these topics here, the first 3 topics that appeared on the archive last week by Annabelle Bort and collaborators. Okay, so let's start with 1D systems. We're gonna very lightly dope a 1D system. And first, let's look at what happens in equilibrium. So here is an antiferromagnet, and we're gonna insert one hole into it. And the question is, what is the ground state in this case? Would it prefer, there are 2 possibilities here around the hole. Would you prefer to have the spins aligned around that hole, or would you prefer to have them anti-aligned? And so let's now, in order to lower the energy, the hole wants to tunnel. And once it starts to tunnel, you can see in this situation here where the spins were aligned, you will immediately create this unsatisfied bond here, this J. Okay. While in this situation, the hole just hops happily. So clearly this situation is preferred. You would rather have the spins to be anti-aligned around the hole. Okay, so now we can use the microscope to look for, to evaluate 3-point correlations where we try to find a hole and indeed look at how, to verify that the spins are anti-aligned around that. We already know that when we discussed the phase diagram of the Hubbard model in 2 dimensions, once we doped the antiferromagnet a little bit, the antiferromagnet immediately disappeared. So if you looked at 2-point correlation functions, you would see the decay very rapidly once you dope the system. Now, the same happens in 1D. If you dope the system, the 2-point correlations vanish. But there are, now that we know that this is the picture here, there are ways to bring these correlations back. So one approach is to go to what's known as squeezed space. So what you do is you just cross out all the holes and doublons from the pictures. And then if you look at the remaining spin chain, it will have antiferromagnetic order, as you see here. It will be up, down, up, down, up, down. Okay, so this is the squeezed space picture. You've squeezed out the holes from the system. Alternatively, you can use this is a more mathematical technique, is to use a string correlator. So in this case, so this and this here are what you would be your usual 2-point correlator. So you have SZ on site I and SZ on site I plus D. So this is the correlation at distance D. But now you throw in this product here, which adds in a -1 sign for every time you cross a hole between these 2 spins. So this is this string correlation. So basically the -1 sign is correcting for the shift of the antiferromagnetic order when you insert this hole here. And so you expect, again, this string correlation to bring back the correlations as opposed to the 2-point correlation. And this is indeed what was seen in this Munich experiment. So in blue, you see here the regular 2-point correlator, which dies very quickly with distance. But then if you evaluate the string correlation, that kind of goes a bit more than that. And of course, it's still limited by the fact, it's a 1D system, there's thermal fluctuations, etc.
How many holes are there in these measurements? Is it just one, or there's a finite density?
I think it's. I honestly, I don't remember what they did in the paper, but I assume it's just a very low number per chain. They have full. They have full spin and charge resolution, so they can post-select on data with one if they wanted to.
Okay, thanks.
Okay, so now we can ask what happens with the ground state if you add even more holes, and this is, I think, related to a question Leo was asking in the previous talk. So this starts to get into this incommensurate antiferromagnetism, which is related to FFLO. So if you are at half filling, you remember we had this 2-point correlation function kind of, you have up, down, up, down. It has this wave vector pi. And now once you start to dope the system, then this periodicity will get longer. So basically, these holes kind of form domain walls in between the antiferromagnets. And so the prediction from Lottinger liquid theory is that the wave vector will go linearly with the doping. So this is the density here, and so it would be like 1 plus delta the doping. And so yeah, it changes linearly with the doping. And then you could also ask what happens when you spin imbalance the system, and there's a very similar behavior there too. So now you get again a different modulation. It's an incommensurate antiferromagnet. It's not commensurate with lattice spacing anymore. So
can you go back to that just real quickly?
Yeah.
The reason I'm confused is that at 0 doping, it looks like you have a 0 wavelength AFM,
So
when I would have thought you should get a pi wavelength.
No, so n is the density, so it would be like 1.
Well, okay.
So like if n equals 1, you would get pi, and then if you go slightly away from 1, it would just disperse linearly.
Gotcha. N is the density, not the doping. Got it. Mhm.
Okay, so this is what I was telling you earlier. They have this full ability to resolve the spin and charge. So in this experiment, like each two rows, like here, basically, this box here is one chain. They've just split it into two lattice sites using a Stern-Gerlach. So they've put, for example, the spin ups here, the spin downs here. So this was originally one chain, and just for purposes of imaging, it was split into two chains. And in this experiment, they're actually just, I think, taking data over and over, and naturally there's some fluctuations of the density and some fluctuations of the magnetization in the system. So there's sometimes some spin imbalance happening in the system. And so they just sort the images they get by density and by magnetization. So for example, this chain here is at half filling, n equal 1. It has 0 magnetization. This one was away from half filling. This one was away from spin balanced. Okay, and then what they do is they extract these 2-point correlation function as a function of distance, and you see the blue curve here is at half filling. They get this alternating this wave vector pi, but then once you go away, for example, at density 0.7, this red curve here, the modulation gets slower. And if you Fourier transform it, you indeed observe this linear dispersion with so this is at a particular density of 0.7, you do this at different densities and you observe the linear dispersion. And again, it's very similar behavior with the polarization. Okay, so this is looking at what happens in equilibrium in this 1D system, but now you could, I mean, this is all, some of the stuff is all linked to spin charge separation, this ability to go to squeeze space and so on. So let's kind of probe the spin charge separation, which I'm sure you'll hear about more in, Thierry hasn't spoken yet, right? Yeah, so you probably hear about it more in 1D systems and in Thierry's lectures. So let's look at this spin charge separation more now in a dynamical situation. So let's start from an antiferromagnet and now insert a hole into the system. So this is this brown dot here, and ask what happens. Okay, so this hole will start to move. Okay, and now you see once it has moved, it left behind this domain wall here. It can move again. Okay, so the hole and the domain wall separate from each other, and they're now, quasi-particles. So the original hole has now broken into something called a holon, which moves at t, and a magnon, this domain wall, which moves with j, with the super exchange, which is slower usually than t. Okay, so we can say that this hole has fractionalized into a spin-on and a holon. It was not a stable quasi-particle, and it broke up. And these holons and spin-ons have fractional quantum numbers. So a holon would be a spin 0, charge 1, while a spin-on would be a spin 1/2, charge 0. Whereas the original hole that we injected would have charge 1, spin 1/2. So it kind of broke into these two components. And I mean, this is not such a spin-on it's a pretty weird object. It's not like the magnons you might be more used to. So a magnon you can create with a local spin flip. It would have spin 1, but here you have to kind of flip the whole chain essentially in order to get this. So you can create it with a local spin flip. You can create it with this sort of dynamical process, this dynamical fractionalization. And I mean, you're seeing this example of spin charge separation here in a simple setting of 1D, but I mean, there's much less well understood versions of it once you go in 2 dimensions with quantum spin liquids. There, people also see things like a spin-on can you insert a magnon can break up into 2 spin-ons, for example. Okay, so now the beautiful thing again is we can observe all this stuff in a time-resolved manner with these cold atom systems, with these microscopes. So this is again work from Munich, and what they did exactly what I described. They inject a hole and then watch this holon and the spin-on spreading in the system. So this is the spread of the hole-on here, and this is the spread of the spin-on. You can probably make out a bit of coherent effects for the hole-on because the energy scales for the hole-on are like this T, so we're cold compared to that. But with the spin-on, the relevant energy scale is J, and the temperatures are on the order of that, so you don't see much coherent effects there. And the key thing to notice here is that, if there's a light cone spreading here, you can fit a velocity to this, and the velocity, if you look at the time scales here, these are measured in the same units. This is 5, this is like 18. So the hole is moving much faster than the spin-on, the hole-on compared to the spin-ons. They move at different speeds, so this is kind of observing directly the spin charge separation. And now you could also ask, can I go and measure, the fractional quantum number associated with a spin-on? So here's an attempt at that. So what they did was they evaluated, the standard technique for measuring this kind of stuff is to look at the fluctuations. So they looked at the spin fluctuations. So this is, so we can take a window function here around side J, which is some sort of Gaussian with they pick in the experiment here a sigma about 1.5. So you take this window function multiplied by the Z operator and you square it. So this is now measuring the spin fluctuations. And already with if you just take a regular chain, no hole in it, there's going to be some fluctuations because there's thermal fluctuations, there's quantum fluctuations in the system. So this is this background gray curve. But then when you do this dynamical fractionalization, you see a little bump here on top, and that bump is coming from the spin-on that site. And you don't see the full. So you in the ideal case you would expect this. The spin-on has spin 1/2, so the square would be 1/4. You don't see the full thing, and that turns out to be a finite temperature effect. All right, any questions so far? Okay, so let's move on from 1D. It seems 1D is too simple. Okay, so let's do now 2D. So in 2D, there are two pictures people use. One is polarons, the other is geometric strings. They turn out to be related to each other, and they're good in different regimes, and whether T is, there's two energy scales in this problem, T and J, and depending on which one is stronger, it's usually easier to do the theory in one theory or the other. So let me start with the polaron picture. So again, we're going to dope an antiferromagnet with a single dopant. So here's my antiferromagnet. Again, I keep drawing these up downs, but those are, it's a quantum antiferromagnet. It's just not an Ising model here. We can throw in a doublon or a hole. In this case, in the experiment, they used a doublon. The main reason was, when you image, you always get sometimes these, due to the finite fidelity of the imaging, you sometimes lose some atoms and you get holes. So to avoid that contamination here, they were using a doublon. Okay, so let's now try to move the doublon around. So here it's moving to the right. And if this was just a 1D system, you just had what we had before, right? You have this this domain wall, the spin-on here, and a hole-on. But now this is in 2D. So not only have you made this bond unhappy, you've made all these bonds around it also unhappy. So as the doublon moves around, it leaves in its wake a whole string of unsatisfied bonds. And so there is, if you wish, a tension that grows linearly for the string with distance due to these due to the exchange energies that are appearing in here. Okay, so essentially, two things are competing here. There's the delocalization that you want to happen because of the tunneling, but that's competing with this magnetic energy. And so the result is this, when you have this hole or doublon, you have a localized distortion of the antiferromagnet around this doublon or hole. And this is what we call a polaron. And now with a microscope, you can go and image this polaron in real space. Okay, so what do we expect? Let's look at the background antiferromagnet far away from the doublon. So if you look at the diagonal bonds, like these two here, those are aligned, right? So you expect a positive correlation along the diagonal. While if you, around the doublon here, you see they became anti-aligned. So you expect a negative correlation. So you'll find that around the polaron, the diagonal correlation goes from positive to negative, okay? And that is indeed what was observed here in the experiment. So, basically from the images, you can evaluate now a 3-point correlation function where you go and find this doublon and evaluate the spin correlation around it. And these are the spin correlations along the diagonal here. And you see that indeed they're anti-correlated here while they're correlated far away from the polaron. So from this, you can figure out, you know, the polaron size, which is on the order of 1 or 2 sites in these systems. And this is another correlation function here. So this is the bonds along this direction, the nearest neighbor bonds. And again, you see some distortion around the polaron, around the doublon. Okay, so this is just, again, looking at equilibrium systems. You can now do a dynamics experiments. This is from Marcus's group. So what he did was he has much larger systems, and he's also at lower temperatures. And now what he did was the main drawback in his experiment is he doesn't have the full ability to resolve both the spin and the charge. So he's just looking at total density in the experiment, and he's going to poke a hole in the Mott insulator and watch how this hole spreads. Okay, so this is the size of this hole versus time, and you can see in the beginning this hole just spreads ballistically. But then, I mean, this is only for one tunneling time, so it hasn't noticed that it's moving in an antiferromagnetic background yet. But then once it notices that, it slows down. And so it switches over from this ballistic behavior to a more diffusive behavior, which can be modeled using propagation of a fermion in a beta lattice, ignoring even the antiferromagnet. You can just move around in this beta lattice, and you can recover this. You can get diffusion with something that matches quite close to the experiment. Although the experiment, the hole grows even more slowly, and the understanding there is that could be because of now this magnetic polaron that's appearing. So once you've dressed the antiferromagnet around. Once you've dressed the hole with this distortion of the antiferromagnet, now it moves with an energy scale J. So in this experiment, what they did was they changed J by changing the interaction energy. So they half J, say, between the blue points and the green points, and you can see it slows down. And they take this as evidence for possibly a magnetic polaron. Any questions so far?
So I going to this calculation you were just showing, the beta lattice and things, I seem to recall there was some story of actually, this was from like the Prokofiev paper, if you know the one I'm referring to. They thought maybe it was like subdiffusive, but then there were arguments of whether it would become diffusive at long times. I mean, I don't know if you're familiar with any of this.
No.
Anyways, I guess I was wondering if this could actually be an indication of some of that subdiffusive behavior that they were talking about.
No, actually, I'm not familiar with that paper.
Yeah, I guess, so let me try to reconstruct this, and I won't try to derail you too much if I can't do it. So I guess the difference between, just a particle diffusing around and the hole diffusing around is that the hole's position is identified by the sort of all the background spin configurations. And so you don't get the same interference that you would if you just had a particle moving around.
Mm-hmm. Yeah, you have distinguishable paths when you have the antiferromagnet, while the paths are indistinguishable.
Exactly. So So actually, maybe that was supposed to give rise to super diffusion. That okay, I don't know. I can't remember all, but there was a paper I remember by Prokofiev and I think Svistanov as well about this.
I think they were trying to mimic this, or they're trying to avoid these interferences by going to this beta lattice essentially over here, and that's what gave them this red line. So this just involved. This has one energy scale here, T, and then, I mean, now they're trying.
The reason I was surprised is because I thought that calculation gave a non-diffusive behavior, but maybe that's what I'm misremembering.
I think no, they claimed it was diffusive, and the diffusion constant is like on the order of the MIR limit. Okay, so yeah, we can look at correlation functions, endpoint correlation functions, but of course there's much more data in these images. You can now actually try to find the string patterns that we've been talking about in these images. And this is something, again, the Greiner group has attempted, but you have to remember they have this challenge that they can only image, they can't image the spin and the density at the same time. So what they did is, like, these are the experimental images. They did what I was describing earlier in work from my group. They blow away one of the spin states. So let's eliminate the red atoms. And let's say this is, doped with holes, this system. There aren't many doublons. I mean, if there are doublons, the parity imaging will convert them to holes, but let's not worry about them. So at this point, you just are looking mostly at, the fermions in one spin state. And now there's something a little bit sketchy here going on. They're going to do some post-selection. You can be happy with it or not, but so you have to remember, these antiferromagnets have, they're Heisenberg antiferromagnets with an SU2 spin symmetry. So what they did in this paper was they post-selected on pictures with a high staggered magnetization, so that they start to look like an antiferromagnet in the pictures. Whereas, if they were in the wrong base in the wrong basis, then they wouldn't. So okay, so they've done this post selection, which they claim this is robust against exactly how they do the post selection. But then okay, so now you could go and identify from these pictures what is the dominant antiferromagnet in the pictures, because you can have one antiferromagnet or the one that's on where the sites are flipped. So they identify the dominant magnetization and they compare it to the pictures. And now you can, because there are holes in the system, this would lead to these strings in the pictures. And so you can reconstruct the strings and make a histogram of the lengths, the probability of having a particular length of string. And this is something you could now compare to this geometric string theory that has been advocated by Dembler and others. So this geometric string theory indeed provides a predicted histogram for the distribution of lengths. And what they did in the theory data was start from data from the experiment, actually at half filling, and sprinkle some holes into those half-filled pictures, and then move the holes around randomly to get according to the the histogram that they produced. So they would move them to get the length distribution they wanted, and then they passed them through the same algorithms that the experimental data was analyzed with, and then they found that there is good agreement between this predictions of this geometric string picture with the data that they got for the doped system. So, I mean, there's a lot of creative analysis in here, but it seems to be some evidence from these pictures for these string patterns. Okay, so this is now, I mean, with these strings are when you're going to higher doping, but you can also kind of like start from the polaron picture and ask what's happening to these polarons as we dope the system higher. And so this is going back to the Munich group. So this was the polaron we observed before. And now we're going to start increasing the doping. And what you see is, the pictures are changing. So here they had these correlations which were positive, and they switched to negative at some point. And so they take this point here around 20% where they see this change as evidence for moving from this polaronic regime where you just have a few, a dilute gas of polarons, and then these polarons start to interact, and eventually you go into this Fermi liquid regime. And I mean, they had several. They looked at several signatures in this paper. The takeaway message I want to just point from this picture here, where they look at all these correlations and look at all sorts of theories: exact diagonalization, free fermions, RVB, pi flux, geometric strings. Is none of them are fitting to the data, and it's a really hard problem. All these various theories work in different limits, but there's nothing that captures the behavior of the system across all the dopings. So yeah, we're finally with these experiments in a regime where we don't have theories anymore. Okay, any questions?
So going back to your previous slide, yeah, I think this is really, showing more than one theory in these sorts of things. We're finally getting into a regime where we can reach this promised land of being able to test different ideas. So this is pretty cool. I am curious, so I guess from the simple string picture, it lets us understand about the localization of one polaron or one hole. It also tells us something about how polarons interact, right? So I guess that these pictures you're showing here are in some sense probing the polaron-polaron interactions as well. I mean, maybe indirectly, but there are many polarons in the system.
Not the pictures I'm showing. So these, I think, were pictures where it's just a single hole in the picture. And
okay, this is a single.
Yeah, but they did look at pictures where there are two holes next to each other, and then how the antiferromagnet gets distorted around that, and I guess that would tell us more about the interactions between the polarons.
Mm-hmm. I mean, it seems like I'd be curious on your thoughts on this. For the presumably the binding of these holes is very important for things like superconductivity and pseudo gap, and all of that are potentially important for it. What do you think the best way to start to look at the hole interactions or the binding or any of that is? Do you have any idea?
Well, I mean, the obvious thing to look for would be just hole correlations, nearest neighbor along the diagonal. So far, people haven't observed bunching, or at least, I mean, there are experiments which have seen bunching, but they show this weird behavior where it doesn't show the temperature dependence you expect. Like you would expect it to go away as you increase the temperature. So I don't think we've seen the bunching that's coming as a result of this.
And so you might think that these polaron-polaron correlations would somehow be there, but I guess what they're doing in this paper is they're actually fixing the location of the polarons and seeing how it affects the magnetic background around them. Is that why?
I don't know what you mean by fixing. So they're not fixing the hole. If you just fix the hole in place, then you don't get any of this physics.
No, I mean, they're presenting the magnetic correlations conditioned on one separation of the holes. So presumably you could also take this same data and look at the correlation function of the holes, but you're saying it doesn't look like you'd expect here, the hole correlations?
They do not claim to have seen any evidence of pairing yet. I mean, there's recent theory papers that say if you just get a little bit colder, less than a factor of 2, that you should start to see it.
I think my intuition for this may be wrong, because I would have expected as soon as you start deforming that magnetic background by the presence of the hole, and once those holes both are within the region of that sort of deformed magnetic background, that you should have some signature of binding or anti-binding, just some interaction between the polarons. So it's surprising to me that you can see the deformation of that magnetic background and see holes close together, but not see the effects of the interactions there.
Mm-hmm. I don't know what to say. Okay. All right, so let's see, how much time do I have? Half an hour, good. So yeah, so I'll just wrap up now by giving some future directions. So far we've been focusing on the plain vanilla Fermi-Hubbard model. It'd be obviously exciting to start looking at extended Hubbard models where the interactions are not just purely on site. And recently we took a small step in this direction in my group where we were looking at a model which is not a spinful model. We're just looking at a spin polarized model, which is this TV model. So you see there's no sigma index here. And usually if you look at spin polarized fermions, at these cold temperatures, they're not interacting. So you would just get the tunneling term. But now we engineered an additional term here, which is this interactions between fermions offsite, these spin polarized fermions. So it's single band models. The fermions, you have a single fermion on a site, and it can interact with another fermion on a neighboring site. And the way we did this was using a technique known as Rydberg dressing. So I wanted to present this because it connects to what you learned about Rydberg physics from Antoine. You heard about how these Rydberg atoms have these long-range interactions that are very strong. They might be too strong for what we're trying to do here. So energy scales there are like 100 megahertz or more, and typical tunneling energy scales here are about 1 kilohertz. So if you want to get some competition between the kinetic energy and the interaction energy, you want to kind of bring down this interaction energy between the Rydbergs. So that's one problem. And then the other problem, of course, is that the Rydberg atoms have very short lifetimes. They're typically tens of microseconds, which is, again, very short compared to tunneling timescales. So the solution to kind of utilize Rydberg atoms to get long-range interactions, the solution to both of these problems was proposed a while back. It goes by the name of Rydberg dressing. And the idea is instead of resonantly exciting the atoms to the Rydberg state, you now are coupling with a laser that's quite detuned from the Rydberg state by several Rabi frequencies. And so you're in a dressed regime where now the ground state is no longer the bare ground state, but it acquires a small Rydberg admixture, typically less than 1%. And the smallness of the Rydberg admixture means that you maintain a long lifetime, I mean, at least a few milliseconds. And the interactions are also much weaker. They can be on the order of 1 kilohertz, so they can now compete with the tunneling. So the form of the interaction energy between these Rydberg dressed atoms is now a soft core potential. So it's sort of flat over some range, which can be controlled with the parameters of the light. But the key thing is it can be on the order of a lattice spacing, and it decays then with a 1 over r to the 6 behavior. So we've engineered this model where the interactions are predominantly between neighboring sites. I mean, one of the things we looked at is, again, relaxation of these charge density waves, very similar to the earlier experiments I described. And in this case, we observed, in the absence of interactions, if you start from a charge density wave and allow the system to evolve, it just spreads ballistically. But then if we have these strong interactions introduced through the Rydberg dressing, we observe that the system wants to kind of remain in the initial configuration for a longer time. I mean, admittedly, the times are very short here. We're still limited a lot by the decay from the Rydberg state, but it's the start of something where we can start to see effects of these offsite interactions with fermionic statistics and tunneling and so on. So this is, in this case, the stabilization of the pattern is just coming from the fact that this is an attractive interaction. The fermions just want to stick together here, and the interactions are strong. Actually, this would work even if the interactions were repulsive. The interactions are just strong compared to the tunneling, so breaking the bond costs some energy. All right, so another exciting direction in recent years has been introduction of these bilayer systems. So you've heard how they can be used at least for imaging, to detect the spin and the charge, but you can also do physics in them. So here's some work from Michael Cole without a microscope, where you see in this, he has a bilayer Hubbard system where there's tunneling between the layers and tunneling inside the layer. And he can control the ratio of these two things. So of course, if you turn off the tunneling between the layers, you just get two antiferromagnet copies. But then if the tunneling in the opposite limit, where this interlayer tunneling is strong, then you get singlets along between the layers, and you get a band insulator at half filling of these singlets. And so you can study the crossover between these two. This is maybe the simplest sort of experiment you can imagine with this bilayer system. And of course, I mean, these bilayer systems are now they're being talked about a lot in condensed matter and in the context of twisted bilayer graphene and so on. So it'll be interesting to kind of start going also to other geometries with these bilayers. And actually, that brings me to this slide here, where indeed other geometry microscopes have been realized. So this is work from Peter Schaus at the University of Virginia, where you see he has now his atoms in a triangular lattice. And this is exciting because, you know, unlike square lattices, triangular lattices have spin frustration. So, you know, at large interactions, there's a predicted spiral antiferromagnet that lives in the plane. But then even more exciting is the intermediate interaction regime, where people predict a non-magnetic insulator, which is poorly understood and could potentially be a quantum spin liquid. So this would be something interesting to probe with this microscope.
So there's a question from Eduardo. How could you introduce a twist like graphene in the bilayer?
Okay, maybe that could be done with this system, with the tweezer arrays. I mean, you've already seen, I guess, this holographic tweezers, I guess, with Antoine. He can create like whole, you know, Eiffel Towers and stuff from with his tweezers. So you can do arbitrary three-dimensional structures. So here's something that could possibly do that.
Yeah, I'm super pessimistic about it. I've talked to a few people who have proposed ways of doing this, even overlaying optical lattices. Of course, theorists making these proposals. But all of the twisted bilayer graphene stuff happens at really long length scales compared to the microscopic lattice spacing. And so the effect of tunneling between those sort of moire lattice sites is like 1,000 times less than the bare tunneling. And we're already struggling so much with temperature that I think pushing things 1,000 times colder is probably a really dangerous prospect for us unless we do it in a really clever way. Right?
Yeah. I mean, besides, you know, I think one of the main things, the main things they want out of this twisted bilayer when they twist it is like the flat band, to get the strong interactions, and we have the Feshbach resonances for that, so maybe that's not necessary. All right, so okay, so yeah, I wanted to just wrap up with talking about this tweezer array, since some of you were asking questions about it last time. So this is something that's going on currently in my group, where we're trying to do two things. We're trying to, one, address this entropy problem, try to get to lower entropies, and then to kind of break out of this box where every time we want a new geometry of the lattice, we have to build a new microscope. So we're trying to get arbitrary geometries with this. And it's essentially the same techniques that got introduced with the Rydberg atoms. So you feed an AOM a set of RF tones that produces a set of tweezers. And those are just projected. And so now, compared to the Rydberg atoms, there are a few more things we need compared to them. One is, if we're going to study Hubbard physics, we need the atoms to tunnel between the tweezers. And typically with these Rydberg experiments, the tunneling, the disorder in the depths of the tweezers is around 1% or so. And if you compute the tunneling energy, it's typically about 0.5 to 0.25% of the depth. So clearly they're too disordered to study tunneling physics if you just kind of immediately use them out of the box. But but we can actually fix the disorder because now we can control the amplitudes of these RF tones. And so we've developed techniques to rapidly kind of clean up the array and get into a flat system. And then the other challenge is, of course, with the Rydbergs, they're happy working with atoms that are in many vibrational states. Here we need to be in the lowest vibrational state of the tweezer. And so the technique we're using is a technique that was pioneered by Selim Jochim's group. So what we do is we stick a tweezer, a bunch of tweezers into an optical dipole trap, and you load a tiny Fermi C into this optical dipole trap, 20 atoms or so. And then you just apply a magnetic field gradient to spill out the atoms, and you lower the depth. And you do this until you end up with just 2 fermions in the lowest band, in the lowest vibrational level of the tweezer. Okay, so now you start with, this is our initial state. We can start with tweezers that are filled with 2 atoms. And here's one pattern we tried. This is 4 tweezers. I mean, we can do many more if we wanted, but this is just an example here with 4 tweezers, 2 atoms per site, and the fidelities are about 97% to load into this, to have 2 atoms on a site. So this corresponds to an entropy of about 0.15 kb per particle, which is already lower than what you have in the lattice. This is a classical state here, a band insulator. A classical state, we can easily just look at the atoms and figure out the entropy. It's already lower than what the lattice experiments have, which is about 0.5 kb per particle. But even better, we can actually here we have a link between the number of the fermions and the entropy. So we can bias our tweezers to deliberately not have higher vibrational levels occupied. And so whatever defects we would have in the state are going to be just holes. So most often when we have all this entropy is coming from a missing hole in this tweezer. And so we can just, yeah.
So how are you imaging the difference between 2 and 0? You're doing imaging like Selim does or something?
No, this experiment we couldn't, but we just recently implemented spin result imaging. Like we just split it up. Yeah, but this stuff I'm showing right now was with just the 2s and the 0s are the same.
Okay.
Yeah. So
can I ask maybe a clarifying question? I thought that in the other tweezer setups they have this mechanism where if there's like an even number of atoms, they kind of like hit each other with light and they just like skew up. But here it seems like we want 2 atoms. What is the process that prevents? Is it the fermionic statistics that prevents these kind of lattices?
No, that's what I was saying. The lattices collisions would be there. So like this data here was kind of blowing away one spin state and looking at the remaining. So it's like that's why you're seeing 0 or 1. But now we've implemented a scheme where we just split the tweezer, like use a Stern-Gerlach, put the spin ups in one plane and the spin downs in another plane, and then image them. So they're on different lattice sites. So okay, so I guess one thing I didn't mention was lithium is a challenging atom to image in a tweezer. It's very light. You need very deep tweezers. So what we did was for imaging purposes only, we do the physics in the tweezer, but we just reload the tweezers into the microscope for imaging. And the tweezers are sufficiently far that you don't get the spacing is about two lattice sites. So you never end up with a fermion on the same site. Okay. And then furthermore, we're doing the Stern-Gerlach to avoid, to split up the ups and the downs from each other. Okay, so basically, you can get you can reconstruct the spin and density information in the tweezer array.
So Waseem, just to follow up on that, the two, when you lose the 2 particles due to these light-assisted collisions, this is only a major problem when you're doing the imaging, right? When you're at the lower depths where you can have tunneling, it's fine having 2 particles.
The lifetimes are super long.
It's only when you make the depths really big to do the imaging that it becomes an issue.
When you make the depths really big and you shine some resonant light on them, that's when the light-assisted collisions happen.
Right, yeah, exactly.
Yeah, so so now you can post-select, like I was saying, on images which are, if you have a 7 fermion image, you just throw it away. You look at the 8 fermion, and so you can effectively bring the system down to 0 entropy that way. And then okay, so now this is a boring state. You want to take it into a strongly correlated state. Any entropy you'll have is purely from, the hope from the transformations not being adiabatic, which usually is not a limiting thing. Usually in lattice experiments, the limit is not from the transformations, but from the initial entropy after the evaporation. So to demonstrate some of this stuff, so here's like a simple experiment where we transformed from a band insulator to an antiferromagnet. So we just inserted tweezers in between. We start with an offset and then adiabatically flatten the system, and then you get antiferromagnets. And you see it just perfectly agrees with the theory. There is this weird odd even alteration, but that's expected in the theory and the experiment from like the finite size effect of this chain. And to show you, we can also do dynamics. Like these are cute things we've done where we put we have this chain, we drop a fermion on one end, and then you can watch it go and do things in it. Or here we actually did a SSH model. You kind of arrange the tweezers in pairs, and then it does something a bit funnier in the dynamics. And I mean, there's interesting properties even in the equilibrium. Like if you prepare this half-filled system in the antiferromagnet, turns out, in the SSH model, in the opposite dimerization to the one I'm showing, you would get singlets on these bonds, and then the ends would be these. The remaining up and down would have to be anti-correlated on those. And so you get this funny situation where no matter how long your chain is, you get correlations between the ends. So we've seen that kind of stuff too in equilibrium. Anyway, so okay, so that wraps up this series of talks. So I've told you about a lot of exciting developments with these Fermi-Hubbard simulators. We've talked about transport, ARPIS, conventional measurements, but then also starting to get at the microscopics of these systems with the microscopes. And there's a lot of exciting directions I've mentioned.
Great, thank you, Waseem. So I want to open everything up for questions, especially, so these are just remarkable, I guess, unpublished results you're showing us at the very end here. So historically, I remember talking and writing paper with Cindy Riegel and Adam Kaufman several years ago, doing these tunnel coupled tweezers. And I was always really pessimistic about the sort of platform you're talking about, precisely because the tiniest noise was causing dephasing and things like this. The tunneling rates would be very noisy. But you said you did something technically, and now it just all works beautifully. So can you give us some insights into what you did there to make to reduce the effects of this disorder and noise and things?
Yeah, I mean, Cindy was working with rubidium, which is very nice because you can Raman cool the atoms reasonably well to the ground state, so you have a rapid cycle time for the experiment. I mean, we're doing an evaporation, which takes a few seconds. But I mean, the nice thing is we don't actually need to go very cold. So we actually do a very rapid evaporation because the entropy redistribution is going to happen inside this tweezer when you stick it. It's like a dimple trap. But the key things that this experiment has that the rubidium experiments lacked was, one, lithium is much lighter, so you can afford to have the tweezers a micron or two and have it tunnel. You have the Feshbach resonance. So I mean, the issue they have is, I think all the experiments, most of the experiments Cindy did, I don't want to use the word all here, but they were non-interacting. And the problem is with rubidium, in order to get the strong interactions, you have to crank up the tweezer depth a lot, and then the tunneling is small. But here we can crank up the interactions with the Feshbach resonance. And then there were other technical things like, technical things we figured out how to, I mean, there are two sorts of issues with this disorder. One is you first have to fix it, but then you don't want it to change in time. And we've figured out technical things what are the things that are causing the systems, the disorder to change in time and stabilize all of these things.
Thanks. Yeah, other questions?
Here, I was just curious about the size of the atomic orbitals when you have the shallow tweezers. I guess you said you can make the tweezers shallow and have the spacing like 1 or 2 microns. So what would be the size of the atomic orbital in that case?
You mean the wave function?
Oh yeah, like the one-year function, for example.
Yeah, the 1 year. It's still like I mean, a couple of hundred nanometers. It's not. It's still in a tight binding regime.
I see. And then in that case, is the tunneling energy still about like a kilohertz, or is it?
No, it's a
much
bit
smaller now?
lower. There, I think 200 hertz is kind of typically what we're working with.
I see.
I mean, in the lithium experiments, like for example, from my group, it's typically a kilohertz in the lattice. This stuff is more 200 hertz.
Mhm.
You must have fantastically cold fermions in your adiabatically loaded results if you have an initial entropy of 0.15 and a tunneling rate of a couple hundred hertz.
I mean, what do you mean fantastically cold?
If I translate it into
more
a
than-
temperature,
Yeah, yeah.
it must be like picokelvin or something, right? I mean, it really.
Yeah, yeah.
You should do that. It sounds flashy. So.
When you mentioned that for Rydberg dressing, there was the finite lifetime was a problem. I thought Rydberg atoms have really long lifetimes, so why is that an issue?
I think when people say the word long, what is they mean something like if for example lithium is the ground state is 2s, you excite to 2p, it decays within like order 100 nanoseconds. While if you excite it to a Rydberg state, it lives for tens of microseconds, or if you even go higher, it would be like maybe hundreds of microseconds. But so it's long in that sense compared to the lower states, but it's still very short compared to tunneling timescales, which are milliseconds.
I see.
Yeah.
Other questions?
Yeah, that's why you don't want too much Rydberg admixture in your dress state.
Yeah, so there are also these kind of collective avalanche effects and things with the Rydberg atoms. Is that avoided here just by or geometry or?
Yeah, it's I mean, it's not completely avoided. We still, I think we're getting about a lifetime of about 30% of the single particle lifetime. So we're not getting the full single particle lifetime. But it's not consistent with like having, one atom transfer to a different Rydberg state and you lose the whole sample. It's better than that. We don't have any good theories for why that is. I mean, certainly working with a narrow strip-like geometry seems to help, but I mean, I suspect it's partially lithium. The lightness of lithium helps. So I think what happens is when when you have one of these processes, that atom seems to be just probably ejected, and then that saves the rest of the system.
So I missed this. You said this is a strip geometry. What's your lattice here?
Okay. This is a weird experiment. So it's a two-dimensional system. If you elongate it, it seems, as opposed to like making it, if you make it too wide, sorry. Well, so let me maybe for the students explain what you're talking about with this collective loss. So the standard picture of this collective loss mechanism. So first, I mean, there is a decay rate that you would expect for a single particle with these Rydberg dressed atoms, which is, you say how much Rydberg admixture I have. So that gives you a probability of being in the Rydberg state. And if that probability is small, that your lifetime is correspondingly enhanced. Now, in practice, when you go and do these experiments, you see that the lifetime is actually shorter. And the picture people have for that is that, let's say I am in the 28p state, then there are close by levels which the black body radiation in the lab can couple to. So say you can go from this 28p to 28s or something like that. And now one of your Rydberg atoms in the stress sample undergoes such a black body process, and now you can have sort of a resonant exchange of photons between this particular atom, this contaminant atom, and the remaining atoms in your sample, which are in the 28p state. And this is a, because it's a 1 over r cube process, it's much stronger and it broadens your line significantly. And so whereas in the Rydberg dressing you were detuned by some amount, now when this process happens, this broader, you have a broader line, and so you can suddenly have resonant excitation. And so this kind of process avalanches, and you typically just lose your entire sample. Okay, so there is a so-called facilitation radius for these resonances to happen, and the ideal way to avoid these collective processes would then be to make this facilitation radius less than one site. But what also helps is going from a 2D geometry more to a one-dimensional geometry, because in a 2D geometry, this facilitation radius, like you would have a circle of depth. In a 1D geometry, where you would have 2 points. So that seems to help to kind of go to a more elongated geometry. Anyway, so there's another aspect in this experiment which is also interesting. So with these, to get the large Rabi couplings, in order to get significant Rydberg rest interaction as a system, we actually focus these beams to very tight spots, and that leads to a strong variation of the light shift along the waste direction, but almost negligible change along the Rayleigh range direction. So turns out the fermions are free to tunnel along this direction, but along the other direction, this strong variation of the light shift suppresses the tunneling. So this is sort of a mixed dimensional system where the tunneling is one-dimensional, but the interactions, the Rydberg rest interactions, are two-dimensional. So you can think of it like coupled chains, if you wish.
Was there a particular reason why this sort of geometry of coupled chains was pursued?
No, it's just what comes naturally when you try to focus your laser beam a lot. I mean, we would love to have a box-like beam which just like it's a flat light shift and the fermions are free to tunnel in both directions, but beams are usually Gaussian and things.
There's some really interesting work about coupled chains though, right? Because the different types of perturbations between the chains do very different things. Like tunnel coupling is sometimes a relevant perturbation and interaction coupling is irrelevant. There's a lot of really rich predictions around there that maybe you could explore by taking advantage of that anisotropy.
Interesting. Mm-hmm.
Other questions? All right. Well, we've had a bunch of questions, and it is we are almost exactly right on time. So great job, Waseem. So thank you for all 3 of these beautiful lectures, and we'll look forward to continuing our discussion this afternoon. So thanks, Waseem.
Thank you.
See y'all later.